Let's start lecture 17, and the course is corrosion protection methods, and the topic will be materials aspect for corrosion protection. For the last few lectures we have been talking about effect of composition, and while talking about composition we also talked about the stability of passive film, and we could see that different elements in stainless steel, they have a specific contribution towards the stability of passive film. If the stability of passive film improves as well as the passive film character is impervious in nature, so the corrosion rate will reduce. For example, chromium, if you increase the chromium content, then of course the corrosion resistance of stainless steel will improve, because the stability of passive film is the betterment of stability of passive film happens. Then we also talked about the ease of achieving passivity, like in case of titanium or chromium in acidic medium, in absence of oxidant, we could see that once we connect it to a noble metal like platinum or palladium, we could see that spontaneous passivity is achieved, and that happens because of an increased exchange current density for hydrogen reaction on platinum surface, and that happens during after the once you do alloying little bit of platinum or palladium in titanium, initially both dissolves, and then because titanium has much lower reduction potential than platinum would redeposit back, and it will form some sort of deposit on top of metal, titanium metal, and then the hydrogen reduction reaction will come into picture, and then it will take it to spontaneous passivity. So those are the aspects we have talked about. So now let us talk about some other aspects as per our materials tetrahedron, what we have talked about. So this is related to metallurgy and metallurgical factors like processing related aspects as well as microstructure related aspects. So these two aspects we have talked about composition. Let us see microstructure as well as processing related aspects for corrosion protection. So we talk about processing. Fine. So when we talk about microstructure, it could be single phase or it could be multi-phase. It could be single grained or it could be multi-grained, or it could be amorphous or it could be grained. Fine. When we talk about grained, that means the grain size would also matter. Now that grain size variation could be fine grain to mixture of fine and coarse grain to a very coarse grain, and then when we talk about amorphous, there is no grain. Now there is one more aspect which is single grain, so that means there are no grain boundaries except the boundary between the environment and the material. Okay. So all those cases they will behave differently when you talk about corrosion. Okay. Now if we talk about single phase, that means only let us say alpha grain is present, like alpha brass, or like let us say pure iron, ferrite, only ferrite, or there could be a possibility of formation of austenite. Okay. So in case of stainless steel, austenite will be the phase and it will have single phase, but it can have different grain size. So those cases, depending on the grain size, we can have difference in corrosion behavior. Fine. So let us just see the microstructure part. So when we talk about microstructure, and at the same time we are actually staying in single phase. Okay. Fine. So we talk about single phase, and then there are two variants, multi-phase. So if we talk about microstructure, fine. So there are two parts. Okay. Now, interestingly, so this change in microstructure would also be decided by the kind of processing we are doing. Okay. And at the same time, composition also will come into picture. So, like let us say if it is a plain carbon steel, so then getting a single phase microstructure, you have to go to a very low carbon level. Okay. The carbon level could be of the order of 0.002% weight percent if you consider plain carbon. That is as per our phase diagram of iron carbon system. But that level of carbon is difficult to achieve. So, we have to go up to a double phase, multi-phase region where we can have cementite and ferrite. So, that case it is difficult to achieve single phase, but still roughly we can say at a very low level of carbon we can say that it is mostly ferrite grain, like IF steel, interstitial free steel, where we have a very little carbon, okay, a very little nitrogen, fine. So, that time we can say that it is a nearly single phase microstructure where mostly ferrite grains, but there could be occasional carbide phases also, fine. So, otherwise it may be taken as a single phase. But if you talk about austenite, in case of stainless steel, there we have lot of alloying elements. Carbon is around 0.08%, chromium could be of the order of 18 to 20%, then we have nickel 8 to 10%, but still it can remain in austenite, fine. So, that will be decided by the phase diagram and the composition and phase diagram effect. Even achieving single phase also will be decided by the processing. I will just give some examples. Okay. For example, if we remain in the single phase regime, fine, the single phase can be having several different microstructures, like let us say austenite, or ferrite alpha. Okay. So, it can have fine grain, it can have coarse grain, it can have mixture of fine and coarse. Okay. So, those three variations are possible. Now, interestingly, there is one more variation that can be possible, which comes as, so if it is crystalline. So, here this particular segment will come when this is crystalline, fine. But a single phase regime can have one more segment which is called amorphous. Okay. So, this amorphous structure, or we call it glassy structure, okay. So, that will be a single phase, that means there are no grains, no grain boundaries. So, that is a variation one can have in a single phase regime. Definitely it can be multi-element, okay, it will be multi-element. But here one can get single component also. These variations can be possible. For example, pure aluminium, okay. Pure aluminium, I can get all those variations. How can we get? Okay. So, I was talking about this interlinking between processing and a microstructure. So, pure aluminium, let us say I am talking about pure aluminium, commercially pure aluminium, which is called grade steel, okay. So, 1000 series. So, the pure aluminium here, if we do deformation, okay, after deformation, if we do recrystallization, and then recrystallization can have three variations, okay. We can have recovery, then grain refinement, which is actual recrystallization, and then grain growth. Okay. So, we can get two variations. One is grain growth, and then when we have grain growth, we get coarse structure. Fine. And if we do not allow the material to reach to the grain growth regime, so then we can get fine grain structure. Fine. So, we get two variations like fine grain and coarse grain. Okay. Now, how to get a mixture of fine and coarse? So, there is one particular structure called bimodal structure, where we have mixture of fine and coarse grain. The bimodal structure could be in one case. So, for example, if we draw it schematically, you will see that the grains are very fine, okay. So, if you talk about this is the level of scale, let us say this is 10 micron. Okay. Now, same thing if we take it to the grain growth regime, so it will come like this. So, if you put it same scale as 10 micrometer, you could see that there will be very few grains and the size of the grain would increase. Fine. So, that means we are getting coarse grain. So, this is coarse grain, this is fine grain. Now how do we get the mixture, which is bimodal? We call it bimodal structure. Okay. Now, if we remain in the region between grain growth and recrystallization, so in between zone, we can actually control your grain size. Some grain will expand or grow, some grain will remain in the fine state. Okay. So, then we can get a fine and coarse grain mixture. So, we will call it as a bimodal structure. Now, there and the most of the cases the bimodal structure are obtained by powder metallurgy route, where we can have a better control on the bimodality. That means, we can have a very fine grains and we can have a very coarse grain. All those kind of situations can be achieved. So, there is a particular structure. So, this structure has come up recently, which is called harmonic structure. Okay. So, let us just spend little time on a harmonic structure. So, harmonic structure, it is like this. So, you have a structure like this. So, there are zones with a very fine grains, okay. So, rest of the places we have a very coarse grain. Okay. You could see that these are coarse grain, and these are fine grain. And if you see, if you take a line over it, so this line if you draw, you will see those fine grains are coming repeated as you go along this particular line, okay, in a harmonic fashion. That is what it is called harmonic structure. Here we have a fine grain and coarse grain. How do you prepare it? You take a powder, and that powder already has multigrain structure. Then you deform the surface, do not deform the center part. So, the surface grains are deformed. So, if you sinter it at a high temperature, the surface grains, since they have lot of deformation, so they will go through recrystallization, but the central grain will have a little growth, but it will not have any recrystallization. So, that means if you take a single grain like this, so that means there are, let us say these are the 3 grains. The surface layer, so this surface layer we will have deformation. Fine. So, if you sinter two objects, two powder like this, say another powder with a surface deformation, another powder with the surface deformation. So, now when they sinter, and sintering is done at high temperature around 800 to 900 degrees Celsius, for in case of steel we can go up to that temperature. So, when it sinters, that time this deformed zone will get recrystallized. Fine. And when they join, you will have a structure like the surfaces are getting fine structures, and gradually the grain size will increase from the surface to the inner part will have its own grain. Like that way this harmonic structure will generate. So, that means these zone will go to recrystallization and it will have its own bimodality, that means fine grain and coarse grain, and those fine grains are appearing in a harmonic fashion across the surface and then across the sample actually. So, then we call it harmonic structure. This is actually coming within that segment called segment where we have mixture of fine and coarse grain. And in fact, it has been noticed that stainless steel, if you consider 304 or 316, so their tests have shown that because of this particular very structure, its corrosion resistance improves in 3.5% NaCl solution. In fact, when we have this harmonic structure, it gives you a good degree of corrosion protection. Corrosion resistance improves due to harmonic structure. For 304 stainless steel, when you compare with uniform grain structure. Okay. So, that observation we have seen, and in the next lecture we will show you some of the test data. Okay. Now, we will talk about this fine and coarse grain. Generally, idea shows that when you have grain structure, then if we have those grain boundaries, and grain boundaries are the regions of higher activity, they should get attacked first. And this observation is common in case of iron, mild steel, okay, where in case of 3.5% solution mild steel, it shows that if you have a coarse grain as well as fine grain, the initial attack will be on the along the grain boundary. In fact, this is a common observation in all the materials, all types of materials, whether ferrous, non-ferrous, we see that the grain boundary zones are the first point to attack. So, that is what actually we generate microstructure in steel. So, when we etch the steel, let us say mild steel you have taken, you polish it, metallographically you prepare the sample, mirror polish and then expose to NPTEL, which is let us say 3% NPTEL solution, you will see a fine grain structures are evolving, and that grain structure is coming up because those grain boundaries are actually getting attacked due to the electrochemical reaction with the nitric acid in that NPTEL solution. Fine. So, that means grain boundary is the weak points when we compare the corrosion behavior. Fine. So, then obvious is that grain boundary, if you have a coarse structure, it will have a less attack, and then gradually we should have higher corrosion resistance compared to the fine grain, because the fine grain you have a lot of grain boundaries, so it should attack more. But it is not that simple. Whenever a material shows active behavior in a solution, then or the environment, then generally fine grain shows a poor corrosion resistance, whereas coarse grain shows a higher corrosion resistance, a better corrosion resistance. But it is not uniform like that. There could be a variation depending on the grain boundary precipitates, depending on the types of segregation of elements, or there could be possibility of precipitates along the grain boundary, there could be possibility of elemental segregation along the grain boundary. All those things can come up, and then it might show a different behavior altogether. So then we can say that even if the material shows active behavior in a particular environment, then coarse grain might show a poorer corrosion resistance than the fine grain structure. Okay, we will talk about that part, fine and coarse grain, because it needs a complete discussion specific to different materials like magnesium, aluminium, titanium, nickel, and of course steel. Okay, so we will see that people have shown different experiments that in some cases fine grain structures show a better corrosion resistance, coarse grain structure shows a poorer resistance, or sometimes it shows a better resistance. Fine, we will talk about that later on. Okay, but what is interesting is this amorphous structure. Okay, so let us discuss on this amorphous structure. So amorphous structure is basically, or the glassy structure. So if we talk about amorphous or glassy structure, fine. So here this is also single phase structure, and if we compare a glassy structure and a crystalline structure, so this is my grains, this is amorphous and this is crystalline. Fine. Okay. Now if it is amorphous, we will not see any grain boundaries. Then obvious is, if we expose it to the solution, let us say corrosive, let us say NaCl solution, which is a corrosive. Fine. So that time, since there is no grain boundary in amorphous structure, immediately our sense will be the amorphous would show a very high degree of corrosion resistance. And in actually there is quite a bit of consensus that amorphous structure shows a good degree of corrosion resistance just because it does not have any grain boundaries. In fact, single crystal would also show a very good corrosion resistance because it also does not have any grain boundary. If we talk about single crystal, so that time it is again crystalline but no grain boundaries. Okay. So we have all those atoms are regularly arranged. So these atom positions, I am talking about atom positions, those atoms are regularly arranged in a particular matrix, but there are no grain boundaries. So then it is a single crystal, it will also show a very good corrosion resistance because there are no grain boundaries. But single crystal has got its own application field, but when we come to amorphous and crystalline, we can tend to see a very good corrosion resistance in amorphous because it does not have crystalline boundaries, fine, or grain boundaries. Now the major thing is this would show high corrosion resistance, fine, compared to crystalline. So this will show and this will show poor corrosion resistance. This is a general consensus. Generally, okay. Now, whenever we talk about amorphous, mostly they are multi-component. Okay. In a single element, making amorphous needs a very high degree of cooling rate. Okay. So the cooling rate requirement allows it not to be amorphous, it will always crystallize. But there are multi-component systems where amorphous phase formation becomes very easy. Okay. So there are several reasons for that. It actually itself is a field of study, how amorphous phase forms in a particular material, fine, whether it is a metallic or non-metallic, it does not matter. Okay. But there are reasons for this, how these atoms which are to be remained in, which would like to be in a regular arrangement, which is the stable state, but it actually goes through a particular transformation where the atoms becomes random. Okay. And since it is random, so grains will not form and it will form grain free microstructure. Okay. So for that, in a simple fashion for our discussion, amorphous phase forms in a particular material due to its fundamental reasons. So, reasons why amorphous phase form okay. So, one is multi-component okay. So, there is a competition multi-component if we consider in metallic state, that time we call it metallic glass okay. Multi-component alloy composition should be chosen in such a fashion, there are competition between two crystalline phases, there are let us say A, B, C, 3 component elements are there. Let us say AB crystal tries to form and BC crystal is trying to form. So, then there could be competition between that two, so that there could be a possibility of confusion that which one would try to form. And if you cool it, the melting condition, let us say you melt it, and then when you cool it, and if there are competitions between several other multiple crystalline phases between which one would come first, by the time the system decides, you are cooling it so fast that it does not form, and finally the entire glassy system stabilizes, which will of course form a metastable state. So, that time we call it amorphous structure or glassy structure, fine. So, generally composition is chosen in such a fashion, so that it has a competition between multiple crystalline phases to form, and the second part is mostly we choose it in general close to deep eutectic okay. Generally we call it in a way, we choose it in the deep eutectic. At the same time, we have one more situation where it says that the viscosity of melt should be very high okay. Now, when we have such situations, then generally the composition would try to form glass okay. Let me tell you, this is in a simplistic manner, and I am talking about making amorphous from molten state okay. So, then these three things can actually explain the formation of glassy state. And in fact, when we talk about deep eutectic, it associates with another thing, there is a considerable size difference of elements. Between the elements. So, the size difference would matter, at the same time there could be a negative heat of mixing okay. So, in addition to that, there should be negative heat of mixing, we call it del H mix okay. So, when we have those kind of situations, amorphous phase forms, so what happens, you melt it, then quickly cool it. So, we call it quench, and there are methods, quenching methods like water quench, there could be melt spinning, there could be splat quenching okay. Those are the methods. Even atomization can actually convert the metal, that molten metal, into a solid amorphous phase. Now, we term it as rapid solidification okay. So, this rapid solidification would allow the material to get to the amorphous condition, that means we do not allow any crystalline phase to form. So, if we talk about the viscosity, So, if we talk about temperature, so let us say this is Tm, which is melting temperature. Of the alloy, and its viscosity variation looks like this. Okay. So, this viscosity variation relates like this. Fine. So, this is an N, these are all constant. Fine, and this is typically called fragility. Fine, this is called fragility. So, when we have this viscosity like this, if we reach the viscosity to the level of 10 to the power 12 to 13 Pascal second, corresponding to that temperature, and here I am dropping the temperature because I am cooling. So, that temperature we form glass, and that particular temperature called is glass transition temperature. Fine, and this particular equation we call it VFT equation or Vogel-Fulcher-Taman equation. Fine, that decides how the viscosity variation happens with the decrease in temperature. Now, this fragility term tells whether the material would form glass easily, that means at a slower cooling rate, or the material would form glass at a higher cooling rate. And since we are actually trying to hold the melt structure, atomic structure at a lower temperature when it becomes solid, because at that viscosity level the shear movement of atom nearly freezes, and that is what we are actually holding those atom positions in the liquid state at a low temperature, but that time the viscosity has gone up because of this viscosity relation and it has become a kind of solid structure, okay, not crystalline, the solid structure. So, that is what the typical definition of glass is: configurationally frozen, supercooled liquid called glass. Fine. So, that way, because we are configurationally freezing the liquid which is there beyond melting point when you heat it, and that liquid structure is maintained at a lower level, lower temperature when the viscosity reaches to 10 to the power 12 to 13, where shear movement freezes, shear movement of atom freezes and it becomes a solid. So, that is what this is, a glass with a structure with no grain boundaries, and this D star, if it is a very high, it is a very easy glass former, and if it is low, it is a weak glass former. So, that case glass formation would be difficult, and if it is difficult, there will be possibility of crystalline phase formation. So, we can have a variations there. In fact, that time we can get to the multi-phase structure where we have glass plus crystalline phase, and that time we have a variations like partially crystalline, complete crystalline, and the percentage of amorphous phase can change, and accordingly corrosion behavior would also change. But if we can maintain an amorphous condition, definitely it should give a very good corrosion resistance, and that is the philosophy obtained for making amorphous coating. Okay. So, when we have amorphous coating, that amorphous coating can be obtained by high velocity oxyfuel coating, or we can have plasma deposition. That way we can create amorphous coating on the surface, and then its corrosion resistance can improve few orders of magnitude. So, that is the benefit of amorphous structure and its coating. So, that when we have a coating analysis or coating discussion for corrosion protection, we will discuss more about this, but at least we can sense that if we can have amorphous structure on the surface, its resistance, corrosion resistance would improve. So, and here also we can have several variations, like if it is partially crystalline, amorphous to partially crystalline, in general whenever there is a partially crystalline structure, corrosion resistance drastically drops down, That is a common phenomena, generally it has been observed. Of course, it also is also decided by what medium it is exposed to, as well as what composition is chosen for making the glass, as well as that composition what phases it will form. Those will decide what will be the degree of corrosion degradation, but mostly we have seen that it has been observed that the corrosion resistance decreases with the crystallization in amorphous material, and amorphous material would always try to crystallize because it is a metastable condition and the stable condition is crystalline phase. Since we are actually trying to stabilize one liquid structure at a low temperature below melting, so that means it must be metastable with respect to crystalline state of that material, fine. So, that time corrosion resistance decreases. So, common consensus is glass structure high corrosion resistance and partially crystalline various degrees of amorphous phase okay, corrosion resistance drops. And here how do we apply? Coating. So, if we have a coating, then classic coating on a surface, we can improve the corrosion resistance. So, let me stop here. We will continue our discussion on the effect of microstructure, okay, as well as processing together. Definitely composition also will come in picture, because it is very difficult to distinguish three effects separately. We have to do it in combination of all those discussion, and then you will see the processing will also come into picture. We will show some data as well as results. Those results will show that the processing is also very important, fine. So, we will continue till then. Thank you.